So I would like to thank our sponsor, Texas Instrument, for providing us such a great venue. Thank you very much. And I would like to thank several IEEE societies for helping us publicizing the event. ComSci, EMBS, SBS, CSS, and Young Professional Societies. Thank you all. So Professor Widrow would like to take the questions after the talk. So if you have a very quick clarifying question, you can ask, but please hold to your questions until the talk ends, and then you can ask. We will have a Q&A session after the talk. And because of the TI security regulations, we have to leave the venue before 8:45 p.m. So make sure you leave before 8:45. So yeah, we are very excited to have Professor Widrow here tonight with us. So Professor Widrow, he received SP, SM, and SCD degrees in electrical engineering from MIT in 1951, 1953, and 1956. He joined MIT faculty and taught there from 1956 to 1959, and in 1959 he joined the faculty of Stanford University, where he is currently a professor of electrical engineering emeritus. He began research on adaptive digital filters, learning processes, artificial neural networks in 1957. Together with M.E. Hoff Jr., his first doctoral student at Stanford, he invented LMS Algorithm in autumn of 1959. Today, this is the most widely used learning algorithm used in every modem in the world. He has continued working on adaptive signal processing, adaptive noise cancelling, adaptive antennas, adaptive controls, and neural networks since that time. Dr. Widrow is a life fellow of IEEE and a fellow of AAAS. He received the IEEE Centennial Medal in 1984, Alexander Graham Medal in 1986, IEEE Signal Processing Society Medal in 1986, IEEE Neural Network Pioneer Medal in 1991, the IEEE Millennium Medal in 2000, and the Benjamin Franklin Medal for Engineering from the Franklin Institute of Philadelphia in 2001. He was inducted into the National Academy of Engineering in 1995 and the Silicon Valley Engineering Hall of Fame in 1999. Dr. Widrow is a past president and past member of the governing board of the International Neural Network Society. He is associated editor of several journals and is the author of more than 125 technical papers and 21 patents. He is co-author of the Prentice Hall book, Adaptive Signal Processing, IEEE Press book, Adaptive Inverse Control, and the Cambridge University Press book, Quantization Noise. Please welcome Professor Widrow.
Can you hear me? You can? It works? Good. Well, I'd like to say good evening to good friends, colleagues. I listened to this introduction. I'm wondering who that guy is. I've got a lot of things to tell you. It's going to take a while. It's there. You know, I could go fast and skip a lot of stuff, but I can give you more background, more detail. I might tell you some stories if you like to hear stories. My students always like stories. So I'll start out with a story. How's that? Good? Okay. Well, I received the Doctor of Science degree at MIT in 1956, in June. You know, usual graduation time. The summer of 1956, there was a colloquium that was held at Dartmouth College that lasted the whole summer. And people could come and go as they like. They can speak if they like. Just ask questions if they like. Just listen if they like. Stay as long as they like. When they don't like, leave. So I went with a colleague, the two of us, in the summer of 1956. We went to Dartmouth College from Cambridge, Massachusetts. Spent a week there. And the pioneers of neural networks were there. Minsky and McCarthy. I think Claude Shannon must have been there too. I think von Neumann probably would have been there, except that at that very time he was very, very sick and was literally dying. This was sort of the kickoff of the whole field of AI. And they spent a whole summer there. You can tell the people really didn't know what they were talking about. But that didn't slow them down any. Anyhow, I became interested in how does thinking work? What goes on in your head when you're thinking? So I went back and I kept on thinking about thinking. And I did that for about 6 months. Then I realized that you can't just keep thinking about thinking, you have to do something. The ideas that I came up with about thinking I still hold today. But I realized that if you want to have an academic career, you want to succeed in academia, it'd be the same as trying to succeed in industry. You got to do something tangible that somebody can get their hands around. Correct? Now, I did my doctoral thesis on the subject of quantization noise. I've given a talk to this group on quantization noise a few years back. I probably should give it again because you got lots of new people. But if you know about Nyquist sampling theory, you know about that. You have to sample twice the highest frequency component contained, and then you can recover the signal from the samples. Well, if you draw a curve on graph paper, you can see that there's quantization vertically and horizontally. Quantization in time, quantization vertically. I was able to use sampling theory to analyze quantization. Sampling theory is linear. Quantization is nonlinear. I was able to precisely analyze nonlinear quantization using linear sampling theory. That was my doctoral thesis. I was just a kid. I could tell you all the results, but that would be another talk. So anyhow, I was after I received the doctoral degree, I joined the MIT faculty and was teaching for 3 years before coming to Stanford. And during that time, I was teaching a course that today is sort of a mixture. You call it digital signal processing and digital control systems. This was back in 1956, 57, 58. I knew about digital filters. We described them, we analyzed them. Nobody could build one at that time. But that, thinking ahead. Anyhow, I got the idea, instead of trying to build something that thinks, I thought that would take probably about 25 years, and that was way, way back. We still haven't done it. And I could say another 25 years now, maybe really. I don't know. The idea was to take a digital filter and make the coefficients variable. So in other words, you have a variable filter. And I also knew about Wiener filter theory. See, these are optimal linear least squares filters. It a filter design method that Wiener worked out that allow you to derive an expression for the impulse response of a digital filter that is optimal in the least square sense. Whatever you're trying to do, predict, noise filtering, all these things are Wiener filter problems. So what I thought of was this. I knew when I studied Wiener filter theory, it says in order to design the Wiener filter, you need to know the statistics of the input signal. And you've got a real problem in the real world. Who's going to give you the statistics of the input signal? The input and the desired response, you need to know the cross-correlation between them and the autocorrelation of the input. You plug that into Wiener's formula and you got an optimal filter. The only thing is nobody gives you the statistics. So I started thinking about that, and I say if you allow an input signal to flow through the filter, you can adjust the coefficients. If you can measure the error, you can adjust the coefficients to minimize mean square of the error. And I was using gradient methods to do that. And that's what's used today in the backpropagation algorithm that everybody is using with machine learning techniques. So we were doing that. We were actually able to simulate some very simple, small digital filters. We had an IBM mainframe at MIT at the time. But you can put 100,000 of those today in your wristwatch. But that was a powerful, powerful computer. So we were able to demonstrate simple learning in a digital filter. Instead of trying to build something that's intelligent or smart or this or that, how about something practical, simple? Just a digital filter that's capable of learning. Or at least adjusting itself, self-optimizing. So that's what we did. Then in '59 I came to Stanford. And I'd just gotten there at Stanford. I was in my office. I got a phone call from John Linville, who was a very senior faculty colleague in electrical engineering. And he was telling me about a student that he has named Ted Hoff. And Ted Hoff, he said was a really, really bright guy. He'd love to have him as a student, but he doesn't seem to be interested in what I'm doing. Maybe he'd be interested in what you're doing. He says, would you be willing to talk with him? I said, sure. So he came over to my office and we had a little talk. It was on a Friday afternoon in the fall, the autumn of 1959. I was up at the blackboard explaining how the gradient works and how you make a digital filter. But I knew also that you can use this with neural nets because one of my students at MIT was very interested in artificial neurons, and his interest was in doing logic. Today you call that threshold logic. So he was very interested in that. He wasn't too interested in learning, but I was. But anyhow, he got me involved with neural nets, and I could see that the basic neural element is a linear combiner. And what you have with an adaptive filter is a tap delay line with signals at the taps connected to weights that are then summed. And the linear combiner, what the adaptive filter was a linear combiner attached to the taps of a tap delay line. And the neural element was just a linear combiner with a nonlinear device at the output of the sum. So if you can train one, you can train the other. So anyhow, I was describing all this to Ted Hoff up at the blackboard, and somehow out of the discussion came an idea of a very, very simple way to get a gradient estimate. And the gradient estimate was the secret sauce of what we now know as the LMS algorithm. So Hoff and I never called it that, but my subsequent students began to think that's a good name for it. So that's what we called it. This algorithm is now used in every modem in the world. It's the most widely used learning algorithm. And it's technology from 1959. Not too bad. I suspect 100 years from now it'll probably still be used. We never were able to prove that it converges. We had a whole bunch of convergence proofs, but they were based on all sorts of assumptions about the input signal. So, but when you go out in the real world, the assumptions are not strictly met, but the algorithm still converges. When we first published this, I was getting phone calls from all around the planet in the middle of the night. People want to know why it doesn't converge. You know, and when I heard that, my heart sank. But, you know, after a while, people realized that if they put this on a computer and wrote code, there's something missing in the code. You didn't do it right. And once you did, see, the way it works is that once you do this and make it work, it'll never fail you again. But you have to get it right the first time. So anyhow, that day, it was a Friday afternoon. I remember that because the next day was Saturday. It was the end of the day. See, that time the EE department at Stanford had a stock room, and you can go in and check out electronic parts and build little stuff. And nobody asked any questions. But the stock room was going to be closed. The next day was Saturday. So we went downtown Palo Alto to Zach Electronics, and we bought a whole bunch of parts. And we're going to put together a simple learning system. We actually made it work first on an analog computer. Hoff had it programmed on an analog computer. About a half hour after I wrote the first equations of LMS algorithm on the blackboard, he had it up and running on an analog computer. So the next day we got the parts. By Sunday afternoon we had it all put together, and I had this thing sitting on my desk, and I can demonstrate a learning machine. Still works. So we made nicer versions of it right here. See? This is from 1959. Still works. Whoops. Still used to work. I could demonstrate this to you, but that would take quite a bit of time. What I'll do is I'll save it, hold it, if people want to see it, and want to see what electronics looked like back in 1959. I've got it here. On this one, the weights. Well, I'll show you what it is. Anyhow, you're going to see a picture of this in a few minutes. So these are the weights. You feed input signals, input patterns with the switches into the weights. And the weighted sum is displayed on the meter. So you train it to give the responses that you want. And I don't know whether I should take the time to show you a little bit of it, but let's hold off and let's see whether we need it. If I needed to explain everything to you. So this is the people involved in developing this idea. I'll have to tell you another story. And we got, for For years and years and years, I had heard about Hebbian learning. And I always thought this was kind of stupid. What I mean is, you know, what the sing-song about Hebbian learning is neurons that fire together, wire together. So if that's the reason why you wired them together, because what it means is when they're talking about wire together, they're talking about the weight increases. In other words, the coupling between them, that weight increases if they fire together. What the heck does that have to do with any practical purpose? So I never paid much attention to it. And about 5 years ago, I was looking at one of the IEEE transactions, I forgot which one. And I saw two articles, one right after the other, of people building hardware to implement Hebbian learning. I'm saying, what the hell are they doing that for? But you know, you figure it out. They're smart guys and they went to a lot of trouble. So I said to myself, I better take another look at Hebbian learning to try to see if there's something to it. And so that's how this subject began, this whole subject of an algorithm that we now call Hebbian LMS. So it's Hebbian learning implemented with the LMS algorithm. And it's only recently that I saw any connection between them. So it took me about 4 years to cook up Hebbian LMS algorithm. I'm slow. But I had to read a lot of literature in the neurobiology, which is pretty awful. You should try to read it. It's just, you know, aside from the jargon, which when you read the jargon and the terminology, it's like reading a foreign language that you don't understand. But if you keep fighting with it, and a lot of it is contradictory, you can slowly make out some things, and I hope to be able to tell you about how neuron works, a living one, how a synapse works, a living synapse, how does the weight change, what's the purpose of it. And I think that this Hebbian LMS algorithm may very well be the way that nature changes the weights in living neural systems. So you see what I have to tell you. See what you think. So anyhow, here we have input signals. We call it the input vector, input pattern, a set of weights, and a sum. And this is the sum. And you go through a quantizer, and that gives you an output. With this type of quantizer, the output would be +1 or -1. Now, in training this thing, you have to supply a desired response. And the question always comes when you're using these things, where on earth do you get the desired response? Because if you had the desired response, why do you need this thing? Right? But the way we were using it is we were training this thing to give binary decisions. So we fed in a set of input patterns. Some of the patterns, we trained this to give a +1 output. And the rest of the patterns were trained to give a -1 output. So you have a set of training patterns, and for each training pattern, you know what the output is that you want. In other words, you know the desired response. So you feed that here. You compare the desired response with the sum, the actual response. The difference is an error signal. And what you're going to do is adjust the weights to minimize the mean square of the error. So what you'll end up with is a converged system that produces an output here, which is the best least squares estimate of the desired response averaged over a set of training patterns. There was, when we were doing this, Well, here's the LMS algorithm. Let me just tell you what that is. It says the next weight vector equals the present weight vector plus the change. And the change is proportional to 2. And mu is a parameter that determines how big the step size is in proportion to the gradient estimate. The gradient estimate is 2 epsilon x. So if you take the instantaneous error signal, multiply it by the x vector, that gives you a gradient estimate vector. Gradient is a vector. And what you're going to do is to add that to the present weights to get the next weight vector. Now, if the error is positive, these are 2 and mu are scalars. If the error is positive, you add the x vector to the weight vector to give you the next weight vector. If the error is negative, then you subtract the x vector from the weight vector to give you the next weight vector. So you add or subtract the input pattern from, you add the input pattern to the weights, and you scale it in terms of 2 mu. So if you make mu bigger, you'll make bigger steps, you'll converge faster. But the problem with doing that is that you're using a gradient estimate. The gradient estimate is an estimate of the derivative of the mean square error with respect to all these weights. The mean square error is not what you're using. You're using the instantaneous error. So what this is you're taking the error, and instead of squaring it and averaging it and adjusting these things to minimize the mean square of the error, which is what you want to do, what you do is every time you get a new input pattern, you make a small change in the weights. And the small change in the weights is in accord with this algorithm. The gradient the gradient is instantaneous. It's a very, very noisy gradient. You're taking a single sample of the error and squaring it and saying that's the mean square error. And you know that that's a lie, but you do it anyhow. So if you do that, you get this algorithm, which means that the changes that you make, you think are in the direction of the negative gradient. You want to go down to the bottom of the bowl. So you can show the mean square error is a quadratic function of the weights. So what you're doing is climbing down to the bottom of the bowl to minimize the mean square error. The mean square of the error, what you're using is just a single sample of the error, not the mean square. So the single sample of the error square is a very poor representation of the mean square error. Nevertheless, it turns out to be an unbiased estimate. If you keep following it with small steps, I'm not explaining this very well, but I'm just telling you that this whole algorithm acts like a multidimensional low-pass filter. And what you got is a very noisy gradient. You're filtering the gradient with a one-pole filter. It turns out it takes you down to the bottom of the bowl. So it takes a lot of iterations to do it. You adapt slowly. Here's a picture of Adeline. Right there. We call it knobby Adeline. It's got a lot of knobs. So you have inputs that are, each switch can be up or down. Plus 1 or minus 1 are the inputs. So this switch connects to that weight and so forth. Then there's an extra weight. This is called the bias weight. There's no switch for that. Its input is permanently inputted by plus 1. And now whatever the input pattern is, you can add that pattern to the weights. And that'll make the needle go more positive. you can subtract that pattern from the weights and make the needle go more negative. So if you put in an input pattern, and you can see with the array of lights what the pattern is. If you put in an input pattern, and the desired response is +1, that's about halfway out on the scale. You add this pattern to the weights to get the next set of weights. On the other hand, if the desired response for that input pattern is -1, then you want to go down instead of up. And then you subtract that pattern from the weights, and the amount that you change all the weights is proportional to the amplitude of the error. In other words, the distance between the needle reading and the place on the meter scale where you wish to be. That's the error. So anyhow, this we built this thing in 1959. Was able to demonstrate it. We put it in a plastic case so that if you take it on the airplane, somebody can look inside and see that there's no bomb in there. So here we have the linear combiner and the quantizer, and there's the output. So that's the same as the previous slide. The difference is, now this is the error. We're getting a desired response from the output of the quantizer. We're saying that the quantized output is the true desired response. And we're comparing this with the desired response to get the error. Now what's going on here is, I'll go back. Back in 1959, 1960, around in there, I've forgotten. Playing with this guy, I was putting in patterns and training it to do what I want. But sometimes I put in a pattern and said to myself, suppose you don't know what the desired response is. So what I thought was, I'll look at the meter reading and see whether it's reading positive or reading negative. If it's somewhere on the positive scale, then I'll assume that the desired response is +1, which is in the middle of the scale. If the meter is reading 0 like this, I would adapt it to bring it up to +1. If it's reading higher than +1, I would adapt it to bring it down to a +1. In other words, if I put in a pattern and the meter is reading plus, then no matter how big it is, I assume that the desired response is +1. So I train it accordingly using, in other words, I'm using the output of the quantizer as the desired response. So we're saying this thing, like we called it Bootstrap Learning. It's learning by its own bootstraps. I had no particular application for it. It was just interesting. And here's a diagram that shows you how it works. There's a straight line with a slope of 1. This is the quantizer. This is the sum. So when the sum is positive, I assume the desired response is right here. If the sum is down here, it'll push the sum up toward this. If the sum is too high, it'll push it down. So it'll push it up, push it down. This is an equilibrium point. So I go ahead and train this thing with input patterns. Usually, I start out with random initial weights. Usually, whatever response a given pattern had at the beginning, there's a higher probability that it would stay giving that response. But in the course of training, some of the patterns that were on the right-hand side got kicked over to the left. You'll see some of that. I'll show it to you. So this is a picture of the error as a function of the sum. This is another way to look at the previous slide. This is an interesting application. When I was playing with this thing at Stanford, there was a man at Bell Labs. This was the original Bell Labs, the one with Shannon and Bodie and the guys that came up with information theory and the transistors and a few other little things like that. A man named Robert Lucky. You know about Robert Lucky? He was lucky. He was more than lucky. He's a very smart guy. You might see, sometimes he writes a column in Spectrum. So you might see, I think the latest issue had a column. I forgot what the subject was, but I read it, by Robert Lucky. He was working at Bell Labs. Came up with the idea of what's called the adaptive equalizer. So he ended up using LMS Algorithm to adapt his adaptive equalizer. This adaptive equalizer, the principle, is what's used in every modem in the world. It's a basic technology of the internet. Without this, you wouldn't have an internet. So let's see what we've got, and let's see how it works. You're transmitting binary data into a telephone channel. So this is a transmitter. This is binary data stream. You're transmitting pulses into the telephone channel. The pulses are either positive pulse or a negative pulse. Now, if this were a perfect telephone channel, it would be a low-pass filter. It would be ideal. It would be perfectly flat response from 0 frequency up to 3 kilohertz. And then it would drop like a rock, kaboom. So the frequency response would be flat, the phase response would be linear. Now, if you had such a telephone channel, if you put in the unit impulse, the output would be a sync function. Correct? Now, if you transmit data pulses at the Nyquist rate for that channel, then you'd get out, you put in a string of +1, -1 pulses transmitting data. What you get out is a string of sync functions. They're overlapping, but if you strobe it at the receiving end, just where the sync functions are having a peak, a particular sync function has a peak where all the neighbors are having zero crossings. So you can picture a sync function with uniformly spaced zero crossings. So it would be possible, even though the pulses are distinct going in, they're overlapping coming out. But you'd still be able to interpret and get back the data train by sampling at the Nyquist rate, right at the peaks of the sync functions. If you did that, you'd be able to reproduce but now the telephone channel doesn't turn out to be nice like that and give you nice sync functions. The telephone channel is, let me pick out a good English word, crappy. The telephone channel was designed for voice, not data. So what the trick is to take the output of the telephone channel and run that through a filter. This is a digital filter. And notice that it's a linear combiner, a familiar linear combiner. The telephone channel, let's just think of the magnitude response. It has peaks and it has dips. It's not flat. So where the telephone channel has a peak at the receiving filter, this is a filter that's capable of filtering that signal. So where the telephone channel has a peak, you make this filter have a dip. And where the telephone channel has a dip, you make this one have a peak. So that when you cascade this filter with the telephone channel, the product of the two transfer functions comes out essentially flat, and you're basically getting out, at this point, sync functions. Now, how do you make this work? Well, if the channel is not too bad in the first place, if you just put the output of the telephone channel into the filter, you start out setting all the weights 0 except the first one. You make that 1. We having trouble?
Yeah, that's right. Sorry to interrupt.
No, that's good. Is that better? Yeah. A little less noise? It's always the problem, isn't it? Signal to noise. So, you get out a train of sync functions, positive and negative ones right here, if this is adapted right. So you start out with these weights 0, make the first one 1. So now you're not doing any filtering at all. Now you're quantizing the output, and you're getting out plus 1s and minus 1s, and you're looking at the data stream there, and if the telephone channel is not too bad, this thing will just start out. Maybe 90% of the outputs are going to be correct, and 10% are wrong. But if 90% are correct, what you've got is a desired response, which is noisy. But because you adapt slowly, it averages out. And you can start out with a transmission that has one error out of 10, which is not very practical. And you keep on let it adapt, and pretty soon it's making 1 error out of 10 to the 10. Now you can use that for your bank account. So that you see the quantizer. This is exactly like what I was doing with Bootstrap Learning. You're using the output as the desired response, comparing the sum to the desired response. That's the error signal. And you're using that and adapting the weights. Without equalization, this is typical output of a telephone channel with data being transmitted. This is the output of the adaptive equalizer. That's a plus 1, that's a minus 1. Pretty good, huh? Which one would you rather have? So this is Lucky's work. And that's the biggest application of this type of learning, which you call unsupervised learning, because you're not feeding it a desired response. It's using its own output response as desired response. Now, if the telephone line is really, really, really crappy, this thing isn't going to be able to take off in the first place. So what they do today is that when you're first making contact with digital transmission, the first thing you do is you transmit a known sequence. It's a worldwide standard, an IEEE standard, of course. And it's a pulse train that's known. So you know what the desired response is. So you train that thing on that training signal, and then once you train it, then it starts making decisions that are with errors with extremely low probability. So you switch it from training on the training signal over to training with unsupervised. So it's supervised training in the first place when it's training on a known signal. And then you switch to unsupervised because you don't want to keep training it, you want to start transmitting data. Right? Now here is, well, let's go back. Here's this. Whoop. I'm pushing the wrong buttons. This is Bootstrap Learning. This is unsupervised learning. Its own output is its desired response. You say, what on earth could this thing learn? It's already made up its mind. But be patient, it's okay. So look at that, and then we're going to replace the signum with a sigmoid. Here's the sigmoid. So it's exactly the same circuit. But instead of 1, this goes through a gain of gamma, which is a positive coefficient less than 1. And let's see what the effect is of this. May not be easy to understand, but it's nice to look at, isn't it? All right, here's the sigmoid. Here's the sum. So if you look at it, the sum is the input to the sigmoid. And the output is the output of the sigmoid. So here's the sum, and this is the sigmoid. So for given values of sum along this axis, the sigmoid output is on this axis, and so you follow the sigmoid. As the sum increases, you just go up that way. See? Now, you have to go back again. Oh, I should say, notice that gamma is less than 1. The slope of that line is gamma. So you take the difference between the sum through the function gamma, a linear function. The distance between that and the sigmoid output is an error. And I'll show you where that is. The sigmoid output is here. You take the sum through gamma and take the difference of the two, that gives you the error. So the error here is positive, the error here is negative. So here if the sum falls within between here and here, the error is positive and it'll push the sum to cause the output of the sigmoid to go up to a stable equilibrium point. On the other hand, if the sum is bigger than the equilibrium point, the algorithm will tend to push the sum back down toward that. Now that business of focusing there or here, in other words, if you put in an initial pattern and the response is negative, then you assume the desired response is here, you adapt it that way. On the other hand, if the response is here, it's negative, but it's too negative. So now you're adapting it toward this point, you push it that way. Now to show you the effect of this focusing or causing things to go to one equilibrium point or the other, depending on the initial conditions. You see, whoops. You see the focusing here and here. That's exactly this. Going to here or to here. See? Now we did an experiment. Random initial weights. Some input patterns produce positive output, which is green. Others produce negative outputs, which is orange. So we have a whole series. We start out with random initial weights. We have a whole series of input patterns. Each one of these crosses corresponds to one of the input patterns. So if you don't change the weights, just put the patterns in. Look to see what the output response is. This is the sum right here. You'll see that you'll get a bunch of responses along here and a bunch of responses along here. Now, when you start adapting, this is after 10 training cycles. And what you see is the ones that were green. One of the orange ones went over on changed sides. And here's an orange one, but notice that a few of the green ones changed sides. So the adapting is doing something. If you keep adapting, you tend to focus here or here. Now, what orange means is that the patterns that correspond to orange were negative in the first place, and they're still negative. But there are a few orange ones up here, the negative that switched over to positive. On the other hand, the green were all positive response, and some of the green switched side, and they're over here. And it doesn't matter. It's going to focus the responses of the training patterns here or here. But the initial conditions, the initial random conditions, have a heavy influence on it, but not absolute. This is with further training, 200 cycles. Things are getting more compact. And this is a learning curve that shows mean square error as a function of the iterations. This curve looks like an exponential, but it probably isn't. We don't have any theory yet to describe, we don't have an expression for that curve yet. So this is mean square error versus iteration. Now, what do you mean by error? What's mean square error? Here it is. Put in an input pattern with a given set of weights, you've got an error. What LMS is doing is minimizing the mean square error. So the Hebbian LMS algorithm is like this. The next weight vector equals the present weight vector plus 2 mu epsilon x, just like LMS. But the error is the sigmoidal function of x transpose w, which is right here. That's the sum. So it's the sigmoidal function of that. That's right here. So SGM of that is right here at the output. And then you've got minus gamma. Gamma is here. X transpose W, which is here. You take X transpose W, multiply it by gamma, and bring it here. That's that. And this is here. And this is what that is. So it's just like LMS algorithm. The only thing is it's a funny way of getting an error. And this is completely unsupervised. It's getting the error from its own output. And the question is, what the heck does that do? What does that have to do with Hebbian learning? You'll see. Oops. Got to get used to this little bugger. You know what I'm going to do? I'm going to get a drink of water. Is that okay?
I'll get it for you.
Oh, it's here. It's here. I have it. Thank you. So what we've got is a layered network. This is a 4-layer network. The inputs come in here. The circles, this represents a neuron. But with a double circle, it's not an ordinary neuron. It's a Hebbian LMS neuron. The ones at the output are supervised, to give you the final output classification. You're going to apply input patterns here. You're going to let each of these neurons train all by itself. They're working all by themselves. It's not like backprop where everybody's talking to everybody else. Here, everybody works by himself. Rugged individualists. Republicans. Now, these aren't Republicans. They got invented by a Democrat. So you feed in the set of input patterns, and these begin to train, and then you keep feeding the input patterns over again, and the first three layers are all Hebbian LMS, and they all train all by themselves. You don't supply any desired response to them. Just start out with random initial conditions and let her rip. Now at the final output, take the output signals into a given layer, and this says softmax, but the way we typically do it with Hebbian LMS is a one out of many code. So you feed in an input pattern, you train the output. Each one of the output neurons corresponds to a specific pattern class. So you have as many output neurons as you have classes. So you train this thing by feeding in an input pattern, and that pattern, you're training it, so the whole system is supervised. But the first three layers are unsupervised. So they act like an unsupervised preprocessor before you go into the supervised layer. The supervised layer gives you specific output responses to what you want, what response you want for that given input pattern. So you feed in an input pattern, and let's say that input pattern corresponds to this neuron. So you train this neuron to give a +1 output, train all the others to give -1 outputs. So you do that, let's say you put in another input pattern, and that corresponds to this neuron. So you train this neuron to give a +1 output, and all the others to give -1. See, that's how you do it. So you're training the output layer, that's supervised. But all the others are unsupervised. And the question is, what are they doing? Well, what they're doing is clustering. And I will explain that. So you here are clusters, just sketches of clusters. So the idea is at the output of the third layer, which is Hebbian, at the output of that layer, what you want is that if you have a cluster at the input, so think of a centroid and a whole series of patterns all around it, all pattern vectors all around the centroid. What you'd like is that when you apply that input, if this thing is trained properly, if you apply that an input from a given cluster, you're going to get a response here. And if you take another pattern from the same cluster, you're going to get the same response here. So all patterns in a given cluster should be giving you the same response here. And if you put in a different cluster, you'll get a different response here. And what you want is that all patterns in the second cluster give you consistent response here. And that's what this network does almost universally. So you don't care what the response is for a given cluster. All you want is that all the patterns in that cluster give you the same response here. Now, if that's the case, then it's really easy to train the output elements to give you the right identification of that pattern whatever neuron you've assigned to that input pattern when you trained it, that's what you're going to get coming out, not only from the patterns that you trained it on, but also all the other patterns in that cluster. So you train it on a given small number of patterns in the cluster, and you expect it to give you a consistent response to all the other patterns in that cluster. So what turns out that once you come in here, these signals could be analog, but these turn out to be essentially binary. And further you go, more binary. So you got binary inputs, binary outputs. We're losing our battery. Maybe I just have to push harder. You don't care what the binary representation is of a given cluster, as long as it's consistent to all the patterns in that cluster. And then you feed it here. This is trainable, so you can train this to give you any of these output. Can you see this thing? Yeah, it's getting faint. I think this one needs batteries, actually. Well, we'll do the best we can. I think it's okay. So everybody's okay so far? Now, how does that work? Why should all the elements of a given cluster give you the same consistent response here? And then by doing this clustering, by clustering all the elements in a cluster and clustering that into a unique response, you're making the job of the output layer very easy. So the question is, how does this work? In the first layer, you start out with random initial conditions. And initially, we look at the first layer. Each one has different initial conditions. If you look in the pattern space with fixed weights, this separates the pattern space into two half spaces. So it's a linear separating boundary that this does. They all do that, but they all do it differently from each other because they all have different random initial conditions. So if you look at it, suppose you have two clusters, and one of the neurons has a separator like that, another like that, another like that, like, let's see, what am I doing? Like that. This thing is really getting faint. I guess you have to push it with determination. So here are clusters, and this just gives you the idea. You think this will work?
As a laser pointer, not for a pointer.
Oh, for the pointer. Okay. That's a good idea. How's that? It's got good batteries. I put them in there myself. So here's a cluster with a centroid and all these patterns around it. The difficulty of a problem when you're trying to resolve these things has to do with the standard deviation of the patterns in the cluster. The standard deviation of the cluster compared to the average distance between the centroids. See? So the bigger row, the more spread out these are and the more overlapping they're going to be and the more difficult the problem. So that's a measure of the difficulty of the problem. Okay, now we start out, suppose we have two clusters, and this is one of the neurons. Whoops. Something happened. Something impossible happened. So here's one of the separators. This is another neuron. You see, they're all random initial weights, so they have different separating boundaries. Now, when this separates, the cluster A and the cluster B are well resolved. Here, they're resolved also. Here, they're resolved, but just barely. And here, we have a separating boundary that goes right through them. So that says some of cluster B goes on one side, some on the other. The same with cluster A. So that's bad, but what we need to do is look back at this. And we see that most of these neurons, for a given input pattern, give you a consistent response. If you take another pattern from the same cluster, put it in, you get the same response. But if one of the separating boundaries is right on the boundary line, then for different input patterns from the same cluster, some of these will give you a consistent response with the majority, others will be in error. So in other words, it's like you're getting responses that have errors, and when you go through this layer, you're doing the same thing all over again, but you end up having less errors here than here. You go through another layer, and less errors here than here or here. If you go through, what we found by experiment is that about 3 layers that generally does the job. Question? Actually, they can get you into trouble. They're bad. You don't want more than you need.
And the width should be about the size of the dimension of the input?
Not necessarily. Could be. That's okay. But you're asking good questions. We're still working, trying to figure this thing out. This is a new kind of beastie. So we're not telling you a lot of stuff about it. We're just giving you the general idea, and you'll see for yourself. You can play with this. This is not hard to code up. This has to do with the idea of capacity, but I think just to save time, we'll reserve that. Good practice when you're doing this. We found that there are theoretical arguments for this, but also experimental support. That the input patterns going into the first layer should be normalized to have zero mean and unit variance. So that's not hard to do. The adaptation ratio of each neuron should be, how do you choose mu? So this is 0.1 over a number of the neurons' weights. So this is what you do for all the neurons, all the Hebbian LMS neurons. The Hebbian LMS parameter gamma should be between 0.3 and 0.5. Doesn't matter, it's not critical. But those turn out to be good numbers. The initial weights of each neuron may be Gaussian distributed with zero mean and variance such and such. Depends on gamma and depends on 4. So this tells you reasonable initial conditions. You're going to choose the weight vectors randomly. If you make them Gaussian, you don't have to. But if you do, a good mean square value would be gamma squared over 4. And gamma is You go back to the beginning, gamma has to do with the slope of the line. It has to do with the derivation of the error function. And what all this has to do with is getting the sum responses so that you're not high up on the sigmoid and saturating, but not so low on the sigmoid that it takes forever to get up into the range where you got good action. That's what this is about. But it's not critical. You don't have to do that. This is an experiment that we did. So for different values of rho, 5%, what that means is that the standard deviation of the cluster. Let's see, I forgot to tell you, this is a problem with 100 clusters in 50-dimensional space. The network had 3 hidden layers with 150 neurons per layer. The training set had 20 samples per cluster. And for testing, we used 80 samples per cluster, which is a big enough number to get a good average of how that's working. So with rho of 5%, the error in training and in testing, they just track each other almost perfectly. And get rho up to 7.5%, you're here. So it does very well with the training patterns, but you still end up with a residue of about 3% error on the testing. So in other words, you trained it and then you tested it with unknowns, and that's what you get. And this one, when you get up to 10%, that's a very difficult problem. The training, it trains pretty well, but it doesn't generalize very well. It's a problem where you're beginning to get a lot of overlap in the pattern space between the different clusters. So it's hard to resolve them. What's going on here? It says biological. Where did that come from? Well, let me go ahead a little bit to show you what's up. This is a clustering example, and this is the description of a synapse and how it acts like a variable weight and what's involved with increasing the synaptic strength or reducing the synaptic strength, increasing the weight or reducing the weight. So this is a neuron with a synapse right here. And there's neurotransmitter in the gap and neuroreceptors that are receptors for the neurotransmitter. And I'll describe to you how that works as well as I can understand it. I had to read the literature to try to figure out how this stuff works. It took me quite a while to figure this out and see how to put all this together. What you got here is this. In the living neural system, all the signals are positive. You don't have positive and negative inputs. The output of every neuron is positive. It's plus something or zero. In other words, the neuron is firing. The firing pulses that come out of the neuron are positive. There's no such thing as a negative pulse. So the signals from a neuron that go to other neurons, these signals that are transmitted from one to the other through the synapse, and all signals are positive. All weights are positive. There's no such thing as a negative weight. So how the hell do you make this thing work? Well, we got something here. So let's say we have a set of inputs coming. These are input signals coming into synapses, and the outputs of these synapses, if you're getting output, it affects the sum in a positive way to make this neuron fire, in the direction to make the neuron fire. On the other hand, there are certain other inputs. These are positive inputs. They go through positive weights. So these signals are all positive. But the effect that they have, because of the nature of the biochemistry, has an effect on the sum negative. So you don't have negative inputs, you don't have negative weights. All positive. The whole thing works with positive signals and positive weights. So how do you do Hebbian LMS with this? And I'll tell you, I haven't really told you much about Hebb. I'll have to tell you about that. And where does Hebb come in? Fire together, wire together. You'll see it very shortly. You are most patient. You are very good students. So you have certain synapses that are called excitatory, and other synapses that are called inhibitory. So the signals from the inhibitory synapses, when they come into the neuron, so I'll show you how that. The signals from the synapse, you have a neurotransmitter, then you have receptors. So when neurotransmitter gets attached to a receptor, produces a signal that affects the soma, the nucleus of the neuron. This is the sum. So you're getting a signal through here, through the neurotransmitter. You're getting a signal through all of these dendrites. The output signal goes through the axon, this way. What you've got in the neuron is a pulse generator that will generate pulses at a variable rate depending on how high the input is to the pulse generator. So there's also a threshold that the sum has to become positive enough to cause this pulse generator to stop pulsing. And if you make this more positive, it'll pulse faster. So the signal that goes out is either 0 or plus, and how much plus has to do with the PRF, pulse repetition frequency. How fast are the pulses coming? That's the signal. So the signal comes into the synapses from other neurons. And the amount of signal that comes in, you're getting, this is connected to another neuron. When that neuron fires, it causes a signal to travel down, and right here, on this side of the synapse, there are what's called vesicles that emit neurotransmitter. And every time a pulse comes along, a certain amount of neurotransmitter is injected into the gap. How wide is that gap? It's about 2 microns. So this is a pretty little bitty thing, but you know, in Silicon Valley, that's getting to be pretty gross. So I'll tell you more about the neurotransmitter and the receptors, and whether the weight increases or decreases, and how that relates to fire together, wire together, and how that relates to Hebbian LMS algorithm that's unsupervised and does clustering. So we'll back up a little. So here we have, if you look at this, you can see this is Bootstrap Learning. And the fact that we got this doesn't have any effect on that. So the learning algorithm here is exactly the same as what we saw before. The only thing new is that the inputs are all positive, the weights are all positive, but some weighted signals act negatively on the sum, some act positively, excitatory or inhibitory. Now the output of the sum is from the axon, that's the pulse generator, and that's producing output pulses that go through, this is a sigmoid, but it's a half sigmoid. In other words, if the sum is positive, you're up here on the sigmoid, you produce output. If the sum is negative, the output of the sigmoid is 0. In other words, you're not firing. So in order for the neuron to fire, the sum has to be positive. If the sum is negative, the neuron doesn't fire. It's not quite that simple. The threshold, the breakpoint, is at a voltage of minus 70 millivolts. So if you're more negative than minus 70 millivolts, the neuron doesn't fire. If you're above minus 70 millivolts, the neuron fires. But for simplicity, just say, if the sum is positive, it fires. If the sum is negative, it doesn't fire. That's not quite the whole story, but it's close enough. So if you get output, that means that this neuron is fired. Get no output. So if this adds up to a negative quantity, you get nothing out. If it adds up to a positive quantity, you will get out. And how much you get out, how strong the output signal is, depends on how positive the sum is. So this is the same learning process, the Hebbian LMS algorithm, where this is the desired response, and you're taking this and comparing it with the desired response to get the error. And this is Bootstrap Learning with a sigmoid, same as before. The only thing at the output, instead of taking the output here like we did before, we take it here. So this is a rectified version of that. So this is okay. This is Hebbian LMS, sort of biological. Why is it biological? Because all the signals are positive, all the weights are positive, and you have excitatory synapses and inhibitory synapses, two different kinds. They have different chemistry. I forgot what all the chemistries are, but if I told you, like dopamine, melatonin, some of those are the neurotransmitters. So there's a whole family of excitatory neurotransmitters, another family of inhibitory ones. And the receptors respond to the neurotransmitter molecules. So when a molecule gets attached to a receptor, the receptor gets all excited. Says, I found my mate. And it puts out a signal that goes here. And contributes to the sum. Now you have, how many synapses do you have coming into a neuron? It varies all over the place. But typically, it's about 10,000. So you got 10,000 circuits coming into a single neuron. Simple, no? It's the damnedest thing. So this whole neural net, I picture it as sort of randomly wired together. It's not arranged in nice layers like the way we simulate it. It's sort of all randomly interconnected. And the Hebbian LMS algorithm will work just as well with a randomly wired neural net as it does with a layered net. Well, so here is a diagram of Hebbian, and this is an example to show you, illustrate clustering with that funny algorithm with the half sigmoid, just to demonstrate that it does work. It works just like the other, except that when you're doing engineering, you're not going to use a half sigmoid. You use a positive, negative, it's simpler. And but if you're trying to represent something natural, and you have to take into account the fact that the signals are all positive, the weights are all positive. Okay? Now, here is a bunch of inputs. You can see visually that these are clusters. So this is a clustering example. 50-dimensional input vectors plotted along the first two principal components of this vector space. You're seeing it plotted along two components. So you see all these things. So you give this to the network, feed it to the network. You don't tell it what these things are at all. You just feed them to the network and say, network, make sense out of that mess. But it's not really a mess. You see, you're seeing it flattened out. In actual vector space, they're probably well separated. It's a 50-dimensional space. So after training with Hebbian LMS, what the system did is it assigned a color to the different clusters. So it realized that this is a cluster and gave it a color. And this is a cluster and gave it a color. And this one is a cluster and gave it a color. And all we did is gave it these inputs, and that's what it made of it. So it assigned a color. Whatever the color is doesn't matter as long as it's consistent. So it assigned a color to them, and it realizes that the color for this group is distinct from the color for this group. Now, here is this is a histogram of the sum before training. This is one of the in the output layer of a 3-layer Hebbian LMS. This is a selected neuron that we picked from the one of the neurons in the output layer. And without training, the different colors correspond to the different clusters. And you're getting responses all over the place. And this is the half sigmoid output, where the output is essentially zero. There's not much other than 0, 0, and 1. Now with training, this is the sum. This is the half sigmoid output. You see that the patterns are now the output responses are here or here, and what to notice is that the colors here are distinct from the colors here. So this is a set of colors different from this set of colors. There's no two alike. I think maybe this one you can see better. This is the half sigmoid output, so it goes between 0 and 1 instead of -10 to +10. So if you look at it, you see that color, you don't see it here. See, there's a green, but it's different. There's a sort of green, yellow. There's nothing like that here. So it has separated them, just a demonstration that you can separate them. And The result is here, where each of these clusters has its own color. So it's figured out how to color the clusters. All you did is fed it a bunch of points. Never told it what to do. Now what's going on here? A little more detail. When the presynaptic neuron fires, every time it fires, you get what's called an activation pulse. This is a pulse train, but with every activation pulse that comes along, a certain amount of neurotransmitter is injected into the synaptic cleft, into that gap. And those neurotransmitter molecules are floating around in there looking for receptors. So there's a certain probability that a given molecule will attach to a receptor or not. The signal, the stronger the signal coming in, the more neurotransmitter you have, the higher the probability is that neurotransmitter will attach to a receptor and produce a bigger signal. So the bigger the input signal is, the bigger the output signal is. But the more receptors you have, that's like a bigger weight that with input signal gets weighted to produce an output signal. Okay? So the number of receptors is proportional to the weight. The weight is proportional to the number of receptors. Now, what causes the weight to increase? What causes the weight to decrease? When the weight increases, the number of receptors increases. In other words, the thing grows receptors really fast. And when the weight decreases, the number of receptors decreases. So some of the receptors disappear. So they appear and they disappear. So you can have a higher weight or a smaller weight. But the weight is always positive, right? So the analogy is to a variable weight. So a signal comes in, gets multiplied by the weight value, and produces an output signal. So this is the synapse, that's a variable weight. Now what makes, how does it know whether to increase the number of receptors or reduce them? Now we need to go to this picture. Okay. That's going to be difficult, but that's all right. Try to quiet down Professor Widrow. Good luck. Are you guys doing all right?
Yes.
This is a long talk, isn't it?
Great talk.
I told you, I have a lot of stuff to tell you, right? Okay, you ready? Okay, here we go. The sum, if this neuron is firing, the sum is positive. And there's a membrane that goes over the neuron and over the dendrites. It's called a membrane. So the membrane goes here. So the receptors are sitting on top of, attached to a membrane. And if we look at the previous slide, this is the membrane, like a drumhead. And the receptors are attached to it. And the way it works is this. The number of receptors is not going to change. The weight will stay still unless there's an input signal. Input signal causes neurotransmitter in the gap. Without neurotransmitter in the gap, nothing's going to happen. But with neurotransmitter in the gap, the number of receptors is going to change, will increase or decrease. Now, if the membrane is positive, the number of receptors increases. If the membrane is negative, the number of receptors decreases. So that's what I learned from study of the literature, which wasn't very easy. To try to find the right paper or papers where they actually describe this. Mostly they're talking about biochemistry. They're talking about the chemistry of the synapse. That's most of the papers. So this shows a synapse, and if this is an excitatory synapse, if this is positive, when that is firing, so you got neurotransmitter present. If the membrane is positive, the number of receptors increases. And what makes this positive is the postsynaptic neuron firing. If the postsynaptic neuron is firing, if this neuron is firing, then the sum is positive. Makes it fire. So if the sum is positive, the membrane is positive, so the receptors attached to the membrane sense a positive membrane that they're attached to. And with neurotransmitter present, with that being positive, the weight will increase. Now what corresponds to this being positive is if this neuron is firing, that tells you that the sum is positive. That tells you that the membrane voltage is positive. So if this neuron is firing and the other one is firing, you're getting neurotransmitter. This one is firing, that means that the membrane is positive. That means that the number of receptors increases. The weight increases. That's Hebb's rule. Fire together, wire together. Now Hebb, who was Hebb? Anybody know? I know. I never met him, unfortunately. He's I don't know if he's still living. He may not be. But let's say he's a Canadian at McGill University, a neurobiologist. And he came up with this idea. I think he might have been one of the first to suggest that learning takes place in the brain by changes in synaptic weight. He didn't call it weight, he called it synaptic efficiency. And he suggested that this increases and decreases, and that has to do with learning. And he came up with the idea that people interpret it, he never said this, but people interpret it as fire together, wire together. Well, getting interested in Hebb, looking him up, we try to see what his papers look like. And it turns out he never published a paper. What he did do is he published a book. I have an illegal copy of it in my computer. The book came out in 1949, just a few years after the Second World War. 10 years later, Hoff and I at Stanford came up with LMS Algorithm. Neither one of us knew about the other. So fire together, wire together. Wire together means the weight increases. If you say unwire together, that means the weight decreases. I have never said anything about unwire. You only amounts to wire together, fire together, wire together. So obviously, if the weight's only increased, all the weights are going to go hit saturation, and you got a very stupid neural net. So you have to have the possibility of weights increasing and decreasing. He never talked about that. So I did. I said, well, if the presynaptic neuron fires, you put neurotransmitter in the gap. But the postsynaptic neuron is not firing. That means the membrane voltage is negative. If the membrane voltage is negative and there's neurotransmitter present, then the weight must decrease, so some of the receptors have to disappear. Now, if you read the literature, it says they appear and they disappear. But it doesn't say give a clue as to what the mechanism is. The only one who ever said anything about a clue was Hebb. Fire together, wire together. But what he never said is, if the presynaptic fires but the postsynaptic is not firing, that the weight decreases. So you're saying unwire instead of wire. Okay? But when you put all this together, what you got is Hebbian LMS algorithm. Isn't that the damnedest thing? Here's our last slide. So we postulate synaptic plasticity. That's what they call it. They call it plasticity. In other words, the mechanism of changing the weight, changing the strength, or what Hebb called the efficiency of the connection. It's today called plasticity. When the presynaptic neuron is not firing, there will be no neurotransmitter in the gap and there will be no weight change. This applies to both excitatory and inhibitory synapses. Incidentally, in trying to look through this literature, it's almost impossible to find any paper that has to do with inhibitory synapses. Almost every paper, 99.44% of the papers have to do with excitatory. Nobody talks about inhibitory. But without the inhibitory, you can't make this damn thing work. When presynaptic neuron is firing and the postsynaptic neuron is also firing, there will be neurotransmitter in the gap, and the postsynaptic membrane voltage will be positive since the sum is positive. And the number of neuroreceptors will gradually increase, thus increasing the weight. This applies to excitatory synapses. This is Hebb's rule. And Hebb's rule was promulgated in his book in 1949. It's accepted by the neurobiology community. Most everybody accepts it, just like people accept Darwinian evolution and general relativity. Now, no absolute proof, right? But it looks pretty good. When the presynaptic neuron is firing and the postsynaptic neuron is not firing, there will be neurotransmitter in the gap, and the postsynaptic membrane voltage will be negative since the sum is negative, and its number of neuroreceptors will gradually decrease, thus decreasing the weight. This applies to excitatory synapses. The opposite of these rules apply to inhibitory synapses. Nobody talks about them. So I postulated that whatever is the case for the excitatory synapses, the opposite has to be true for the inhibitory. When you do that, you get Hebbian LMS algorithm. So basically, that's what I wanted to tell you about. Question?
The biological network is less general than general network with weights that are close by.
Positive and negative. It really isn't less. The biological version isn't really less versatile or general than the usual engineering one with positive and negative.
I mean, if you make the identity.
In other words, they'll work the same.
Well, there must be an advantage because if you take the identity of the positive excitatory or the other kind of inputs, if you make that programmable, you get the general network, right?
Yeah. It's okay. Ask me later. You're asking what my mother used to call a klutz question. That doesn't mean you're a klutz. Your question is a klutz. Okay, who's got? Question?
Dimensional optimization, it's infamous that you often run into suboptima small values and get stuck there. You've never, that isn't characteristic of what you said. Why not?
It could happen. In other words, the initial conditions are not totally non-critical. They're not critical, but if you're way off on the initial conditions, you can converge to a solution that's something with a lot more error than would be possible. So you're thinking of local optimal like with backprop. We don't know enough about it to really tell you for sure.
I guess we have room just for one more question.
Are there equal number of excitatory and the inhibitory things, or can that be different because it's a biological synapse?
I don't know. I don't think that they're necessarily the same number. But you do have to have an inhibitory synapses together with the excitatory to make the thing work. Otherwise, it's just going to saturate. And you'll end up with a stupid neural network.
Thanks everybody for coming in. Yeah, looking forward to see you.
Anybody that wants to see what electronics looked like back in 1959, etc., I'll be happy to show you.